Good morning, everybody. Thank you so much for joining us today at the American Association for Advanced Functional Material Conference for this section of electronic, photonics, and magnetic materials. Our first presenter is Valentina Benfinati. So far, she's not available. So let's wait for a couple of minutes. So once she is up, we will start our session. Unfortunately, our first speaker, Valentina Benefarti, is not here. So let's move forward to our second speaker, Dr. Omapida Paul from University of Puebla, Mexico. He's going to talk on introducing the room temperature supermagnetism in iron and manganese and cobalt oxides spinal nanostructure by nickel incorporation. Mr. Madapal, now the floor is yours.
Good morning, everyone. Can you hear me?
Yes, we can hear you.
Yeah, thank you. So I'll present the work inducing room temperature supermagnetism in iron, manganese, and cobalt oxide spinel nanostructures by nickel ion incorporation. So as we know, the first row transition metal oxide spinel structures have several important applications, as they have multivalent ion contents, which helps them to use as very attractive materials for heterogeneous catalysis. Also, they have been utilized as electrode materials in energy storage devices like supercapacitors, supercapacitor, and lithium-ion batteries also. While most of these metal oxides have antiferromagnetic behaviors, substituting transition metal ions, by nickel especially, induces ferromagnetism or superferromagnetism, which helps them to a very attractive way to prepare superferromagnetic materials of high functional materials too, because these superferromagnetic materials can be utilized in magnetic hyperthermia, drug delivery, guided drug delivery, or as markers, biomarkers, or magnetic resonance imaging contrast agents. Moreover, they are good heterogeneous catalyst, and if we induce superferromagnetism, they can be used as magnetically separable catalyst, heterogeneous catalyst. So those are the advantages of inducing superferromagnetism in these metal oxide nanostructures. In case of monometallic metal oxide nanostructure like cobalt, manganese, they are normally, due to their spin arrangement, they are antiferromagnetic in nature, while iron oxides are normally ferromagnetic. They have ferromagnetic spin ordering. So what we want to do is that incorporate nickel in some certain concentration, to make them superferromagnetic. So we prepare three sets of samples: cobalt oxide, cobalt oxide, nickel incorporated manganese oxide, and nickel incorporated iron oxides. So nickel ferrite, we can say. And characterize their magnetic properties and other textural parameter and morphology to study and understand the supermagnetism induced in them. So the main idea is to not only to induce supermagnetism in this material, to quantify the magnetic moment, or we can say saturation magnetism, how far we can extend to use them in practical applications. So we prepare three sets of samples: cobalt oxide, nickel incorporated cobalt oxide, nickel incorporated manganese oxide, and iron oxide, nickel incorporated. The first two oxides we prepared by glycol-mediated chemical synthesis, where we used ethylene glycol as solvent and acetate precursors of nickel and cobalt, and PVP, polyvinyl pyrrolidone, as structure directing or stabilizing agents. So we mix those solvents, these precursors and solvents and stabilizer, and heated them in a round bottom flux at 170 degrees centigrade for 4 hours. And after that, after reaching room temperature, we dried them, we separated them, washed several times, and dried at 150 degrees centigrade in air In the case of nickel oxide, manganese oxides, nickel incorporated manganese oxides, the same procedures are followed. Only difference is that after getting the dried oxides nanostructures, we air in at 300 degrees centigrade for 4 hours. On the other hand, for nickel ferrite, we used nitride precursors and used also glycine as a reducing agent. This glycine acts not only as a reducing agent, it acts as chelating agents too, to form such complexes, metal ions and glycine complexes, which when this combustion starts near about 600 degrees centigrade, it breaks and forms oxide nanostructures. So how are those oxides? First, we studied their structural properties, or especially by X-ray diffractions. In X-ray diffractions, we got X-ray spectra of all sets of samples. Here we present the XRD patterns of the nickel cobalt oxides with nickel cobalt molar ratio 1:4, 1:3, 1:2, and 1:1. Means from bottom to top, we are increasing nickel fractions. As you can see, with low nickel fraction, all the peaks corresponds to the spinel structures normal as expected, but the peaks are not so sharp, means the crystallinity is not so high. So when we increase to 1:3 nickel cobalt ratio, the same peaks appear with little bit of slightly increasing intensities. But when nickel cobalt ratio is 1:2, apart from these peaks, there appear several other peaks like here, like this. These peaks corresponds to the another phase, the nickel X cobalt 1 - X instead of 3 - X, and oxygen, which has no spinel structure. It is sodium chloride structures. In the case of, but when the nickel is increased more, 1:1 nickel cobalt ratio, again it came back to and spinel structures with no secondary phase. In the case of nickel manganese oxides, same thing we did, 1:4 nickel manganese ratio, 1:2 and 1:1. As you see, up to 1:2, all the peaks corresponds to spinel structures as expected. And this here, the peak intensities are a little bit higher. As we remember, this sample was annealed after growth 300 degrees centigrade at 300 degrees centigrade for 4 hours. So crystallinity is much better. But when nickel manganese ratio is 1:1, means nickel content increased, we got some secondary peaks. Okay, these are secondary phases. This corresponds to nickel metal. Okay, nickel metal and nickel oxide. So this nickel oxide has also sodium chloride structures. These are act as impurities in these sections. But why in these concentrations or in this mole ratio secondary phase appears, we'll understand later. Okay, we'll talk. So in case of nickel ferrite, no problem. It's purely a spinel structure, high crystallinity, sharp peaks. Okay, so in the case of morphology studies in ACM images, as you can see, the nickel cobalt oxide nanostructure, especially we are talking 1:4, which is in pure phase, of course. These nanoparticles are spherical nanoparticles of less than 50 nanometer sizes and more or less good dispersions. But in case of nickel manganese oxides, especially 1:1, why 1:1 I'm showing, I'll tell later. Okay, so nanoparticles are formed, but this material has highly agglomerated particles, which might be due to the thermal annealing we used in these samples. On the other hand, in case of nickel ferrite, nanoparticles are formed, a little bit bigger nanoparticles are formed, and we can see some floppy natures of these structures, which are not well-defined particles. Floppy materials remains, which is very common in the case of combustion, solution combustion or other combustion prepared material nanostructures. In their EDS spectra, as you expect, all the peaks corresponds to the elements appear. However, what I wanted to highlight that in the case of nickel cobalt oxide, this nickel peak, emission peak, and cobalt emission peaks are very close and they are overlapped. In the case of nickel manganese oxides, this manganese and oxygen peaks are overlapping. However, in the case of nickel ferrite, no peaks are overlapping. So this overlapping may cause some problem in their quantification of the elements, okay, content. So as you can see in this table, in these three samples especially, we are highlighting the nickel cobalt with nickel cobalt oxide with nickel cobalt molar ratio 1:4. So nickel cobalt estimated EDS estimated nickel cobalt ratio, okay, molar ratio is coming 1:3.37 instead of 1:4. Same in the case of nickel manganese oxide, instead of 1:1 ratio, we are getting 1:0.72 molar ratio. However, in case of nickel ferrite, we used 1:2 nickel and iron ratio, but we are getting 1:1.94. It's very close to the nominal composition. However, in the first case, as we are expecting that their EDS estimated compositions are a little bit away from their nominal composition. So, to understand the magnetic properties of these materials, especially in these type of crystal structures, spinel structures, we must consider the electron occupancy of 3D orbital electrons and their energies especially. So in the here we are giving only one example here. For example, manganese 3+, okay, ions. Manganese 3+ ions has 4 electrons in the 3D orbital. Those 4 electrons, if we consider that electrostatic field created by the ligand here is oxygen 2- ions, this is spherical, then these electrons will stay in the same state, okay. But if this electrostatic field created by the ligand is octahedral, the splitting comes in the orbital. So only one electron will be staying in upper orbital, upper energy state, and 3 electrons will be in the lower energy state. Means there will be a spin orbit splitting. In the case of tetrahedral symmetry, okay, or if the ligand field is tetrahedral symmetric, then 2 electrons will go up and 2 electrons will go down. To understand this thing a little better, why this spin orbit splitting occurs, we can see this figure, especially in this same example, manganese 3+. So what happens in the case of as the electrons are in 3D orbitals, here in the 3D orbitals, and if the orbitals and the electrons from the ligands stay in the same line, means they are those 2 electrons from the ligand and the orbital are close, which is the case of this state 3D z² and 3z² - y² state. These 2 states, as you can see, the orbitals and the ligand electrons are very close, so they will feel a strong electrostatic repulsion, and which make their energy state higher, so they will go up. But in the case of bottom one, 3D xy, 3D xz, and 3D yz, the electrons from the ligand and the orbitals are little far away, so their interaction energy is low, so they will come the bottom state. So this is why this electron distribution, okay, the orbital splitting comes, and we get spin orbit splitting. However, to understand the magnetic properties of these materials, as our objective was to make or prepare superparamagnetic materials, so we have to understand their how their electrons, cations will be arranged in the octahedral site and tetrahedral site of the spinel lattice. To understand that, we must consider the site preference energy, octahedral site preference energy of the cations, okay, and then we can arrange them in octahedral and tetrahedral sites accordingly. Okay, to get that octahedral site preference energy of each ion which contain in those compounds, spinel structures, here we arrange in this table, okay, their crystal field stabilization energy, all the ions in our compounds. We have only possibilities: iron 2 plus, iron 3 plus, cobalt 2 plus, cobalt 3 plus, nickel 2 plus, manganese 2 plus, manganese 3 plus, and manganese 2 plus, all possible or ions which are there in all three compounds. Okay, and here we put their number of d electrons, and we put here the octahedral site crystal field stabilization energy. Not only octahedral site crystal field stabilization energy, also tetrahedral site crystal field stabilization energies in kilojoule per mole. As you can see, for example, manganese 3 plus, what we are talking about, it has 4 electrons, and octahedral site, octahedral sites in crystal field stabilization energy is about minus 135.6 kilojoule per mole. But in tetrahedral site crystal field stabilization energy is minus 40.2. So the difference is about minus 95.4, which we calculate as the octahedral site preference energy. So as you can see in this table, the cobalt 3 plus, nickel 2 plus, manganese 4 plus, and manganese 3 plus, manganese 2 plus, cobalt 3 plus, and manganese 4 plus has very high, large octahedral site preference energy. So they will try to remain at least 2 octahedral sites. On the other hand, so octahedral sites, so it's very difficult to put them in tetrahedral sites. Here you can see this nickel in the octahedral sites, cobalt 3 plus remains in octahedral sites, but cobalt 2 plus and cobalt 2 plus, cobalt 3 plus can also stay in tetrahedral site, but cobalt 2 plus will stay always in tetrahedral sites. So as we'll see later, this in spinel lattice, okay, how many sites we have? About in one unit cell we have 16 octahedral sites and 8 tetrahedral sites. Okay, so when we put one excess ion in excess, after occupying those states, they are preferable states, octahedral sites, octahedral or tetrahedral, they will be, they cannot occupy the sites and they will form some impurities, as we saw for a certain composition of concentration of nickel cobaltite material prepared, okay, generated nickel oxide and nickel impurities. That will be clear a little bit here in this case. In this case, we are talking or putting the arranging the ions in every compound. In the first case, the nickel cobalt oxide, the second nickel manganese oxide, and third place nickel ferrite. These are the possible ions. As you can see, we have arranged them according to their octahedral site preference energies. In here, you can see nickel 2 plus has high octahedral preference site preference energy, so it will always occupy the octahedral site. On the other hand, cobalt 2 plus has very low octahedral sites preference energy, so it will occupy the tetrahedral sites. And on the other hand, cobalt 3 plus will occupy both. Okay, so in the case of nickel oxide, nickel manganese oxide, both manganese 3 plus and manganese 4 plus will occupy octahedral sites, and manganese 2 plus will occupy tetrahedral sites, and nickel 2 plus will occupy both. In the case of nickel ferrite, nickel 2 plus will occupy the octahedral sites, but iron 3 plus will occupy both octahedral sites and tetrahedral sites. Here we are putting them in the order of their octahedral preference energy. In a one unit cell of in spinel lattice, we are showing how the ions, okay, cations, which are in the octahedral sites and tetrahedral sites. As we know, in one spinel lattice consists of 8 formula unit, and one spinel lattice has 16 octahedral sites and 8 tetrahedral sites. So considering all those things, here we are putting, okay, in unit cell how the ions are arranged, especially in their according to their site preference and their spin alignment. Why you are putting these things? Because not only that, we are putting the possible arrangement of the ions, they are also spins, which will define their magnetic properties, what will present here. So in the top, we are presenting the magnetic behavior, okay, magnetic magnetization curves at room temperature of all the sets of materials. In the first case, nickel cobalt oxides, as you can see, only 1:4 ratio nickel cobalt, this nominal ratios, okay, is giving the perfectly the superparamagnetic behavior. On the other hand, when the nickel composition is increased 1:3, 1:2, or 1:1, we see their behavior is like perimagnetic little bit and with a contribution little bit of superparamagnetic, but their magnetic moment is very low. On the other hand, in the case of nickel manganese oxides, only nickel manganese 1:1, this composition, it is giving your superparamagnetic behavior. Others are like perimagnetic behaviors. In the case of nickel iron oxide or nickel ferrite, we prepare only one sample, but it gave really the superparamagnetic behavior. However, if you can compare all those things, okay, you can see that for a particular fraction of nickel in all those things, they are giving superparamagnetic. Others are not so good superparamagnetic materials. Moreover, in the case of first case, see the saturation magnetization is about 62.5, 62 or 63 EM per gram. In the second case, it is giving about 12.5 EM per gram. In the third place, it is about 30 EM per gram. So to understand why they are a particular composition has superparamagnetic behavior and why, what should be their saturation magnetization or magnetic moment, which is very important for their applications. We are presenting here for this particular composition which gives superparamagnetic behavior only those things 1:4 in this case, 1:1 in this case, 1:2 in this case. So we arrange the cations in their octahedral sites within this square bracket and tetrahedral site in normal brackets. As we can see, how they are the cations cobalt and cobalt ions and nickel ions are arranged, and oxygen is just outside. Okay, only we are interested in cation distribution. So if we consider this type of ion distribution in the octahedral and tetrahedral sites, here we calculate their magnetic moment. So for magnetic moment calculation in this unit cell, what you take magnetic moment of each ion, their fraction in the cell is 30%. For example, it is octahedral site here 30% and it is 70%. Okay, and we have octahedral sites, as I told, there are 16 octahedral sites in an unit cell. So we calculate the total contribution of nickel about 13.6. Okay, Bohr magnetron. It has no contribution. Same thing we did for tetrahedral sites. The cations here in this case, it's about 40% and 60%. Cobalt 2 plus and cobalt 3 plus. We calculated their total magnetic moment. So difference of this total magnetic moment in octahedral and tetrahedral site will give the net magnetic moment that we'll discuss later. Same thing we did for nickel manganese. Same we arranged and their fractions, their octahedral fractions and tetrahedral fractions we consider, and this is the net contribution to their magnetic moment per unit cell. In the case of iron oxides or nickel ferrites, same thing we did, and in the next we are presenting the estimated magnetic moment per unit cell for each of these compounds which gave superparamagnetic behaviors. So here is the nickel and iron ratio is 1:2. I didn't write here, but anyway. So estimated magnetic moment per unit cell we got this much. But as I told, every unit cell has 8 formula unit. So if we divide by 8, we are getting estimated net magnetic moment per formula unit, which should be theoretically is like this. So in the case of cobalt, nickel cobalt 1:4, it should be 3.12 Bohr magnetron. But our experimental we calculated it's coming about 2.82. Okay, Bohr magnetron. Not so close, neither so so far. So what can be the reason of this? Because as you know, at our structures are nanostructures and small structures, small particles. So small particles is high surface, okay? At the spins in the surface have a highly disorder. So spin disorder at the surface will reduce the net magnetic moment. So we are probably, this is the reason that instead of theoretically we are getting every formula unit it should be 3.13 Bohr magnetron, we are getting 2.82 Bohr magnetron. In the second case, same thing we did. This is theoretical per unit cell, theoretical value, and per formula unit you should get 1.4 Bohr magnetron, but our experimental value is about 0.55 Bohr magnetron. So as we know, this material has some impurities. Remember, we have nickel nanoparticles which are normally ferromagnetic, but nickel oxide is not ferromagnetic, is diamagnetic material. So it contributes, so it reduces really. See about 0.55. Moreover, all those particles are very small also. That's maybe the contribution that it reduces a lot. But they are super paramagnetic. That's true. In the case of nickel ferrite, this is the per unit cell theoretical or estimated value of magnetic moment per formula unit about 2.83, but we are getting 1.3 Bohr magnetron. So this material we prepared by solution combustion process, and solution combustion process, as you know, it prepares floppy materials as I shown in the same images, okay, of the sample. So this floppy material has extremely disordered spin, obviously. So that might be the reason. So you have to investigate all those regions and preparing the samples in different other techniques, not solution combustion or like this. So what we are expecting that this floppy materials, nature of this material is the cause for such a low means I'm not comparing with other materials, the same with their theoretical value, the magnetic moment. So anyway, the objective of this work was to understand why and how we can expect why this for a particular nickel fraction we are getting super paramagnetic property, and moreover we are expecting why in some cases we are getting high magnetic moment, in some cases low magnetic moment. This type of research we are expecting to to understand which material we can use for which practical applications. For example, as I told, for magnetically separable heterogeneous catalysis, obviously depending on their catalytic activity, we have to prefer the material. And in this case, if we just focus on that, how good magnetic material is, then obviously cobalt ferrite is nickel cobalt ferrite is the best material. Anyway, we have to probe all those things, other aspects we have to check for their application in biological applications especially, and in case of energy storage application like supercapacitor, we are working, but I'm not presenting here later, but we have seen also that nickel cobalt oxide is a better supercapacitor material too. So finally, in concluding remarks, we can say that we can prepare nickel cobalt oxide, nickel manganese oxide, and nickel ferrite nanoparticles. I didn't give the size distribution histograms, but they have sizes vary from 15 to 100 nanometer size. First two materials we synthesized by solvothermal. We can say solvothermal, glycol-mediated solvothermal techniques. Somebody is telling chemical techniques, somebody telling other things. But anyway, we can tell glycol-mediated solvothermal technique. And next one, last one, though we could have prepared these things, but until now we prepared by solution combustion technique. So in particular composition, 1:4 nickel cobalt ratio in nickel cobalt oxide, it exhibits very good superparamagnetic nanostructures with large saturation magnetizations, okay, and which is much higher than other two oxides, metal oxides. In this case, especially in this composition, we expect this is a promising material for room temperature magnetic hyperthermia, means magnetic hyperthermia applications, especially for biological applications. And in the case of nickel manganite, it has a relatively low saturation, but still it can be used for several applications, especially in catalytic applications. Anyway, all three materials have the potential to be used as catalyst, magnetic super catalyst. Also, some of them can be used as MRI contrast agent, and they can be used as transformer core, okay, core materials, as they are super paramagnetic in nature. So, however, there should be a limit that in case of nickel manganese oxide, we have seen theoretically that calculation that when nickel manganese ratio is molar ratio is 1:1.5 or above, we can get the other phases like nickel oxide and metallic nickel. So you have to be careful on these things. So some of the articles, some of the works, part of the works have been published in these articles. We can consult. That's all. Thank you very much.
Thank you so much, Mr. Murtapal, for your wonderful talk. From audience side, there is no question. I have one question, like, what your anticipated application in future for these like spinal nanostructure, like where you are targeting or something, like if you talk about.
In my introduction, I didn't tell all those things, but anyway, in our laboratory, we prepare all type of materials, nanomaterials. Not only on magnetic nanomaterials, we do work on plasmonics. We do work in semiconductor materials also. We use in energy. Energy means semiconductor materials, plasmonic semiconductor materials we are using as in hybrid solar cells. Also, we use these type of materials, especially relatively magnetic properties. We do study less. We use these materials for supercapacitor and catalysis, especially. So, as you can see, I am sharing the screen, but where maybe here. What happened? Wait a minute. Here. Okay. What happened? I don't know.
Okay. Thank you so much. We are running out a little late. So let's welcome our third presenter, Dr. Rainer Kim from Lund University, Sweden. And he's going to talk about atomic scale surface characterization of optoelectronics, II5 semiconductor nanowires devices. Mr. Rainer Kim, the floor is yours. Yeah.
Yes, thank you very much, for this kind introduction. And good morning, everyone. I'm Rainer Tim from Lund University in Sweden, and here I want to present you our semiconductor nanowires and nanowire devices made of 3,5 materials and what we can learn from their surfaces. And I should go in presenter mode. Sorry, just a second. No, I'm ready. So at Lund University, we do have a strong tradition in 3,5 semiconductor nanowires. What I mean with nanowires is single crystalline materials, typically with a diameter of 20 to 200 nanometers and a height that can reach up to a few micrometers. And we can use these wires for a large variety of applications, reaching really from fundamental physics to medicine. But here today, I want to focus more on electronic or optoelectronic devices and applications. For example, these nanowires can be used in transistors, field effect transistors, where they are used in an upright standing way so that we have such a wraparound geometry, which gives very good electrostatic control. And we can make use of the high charge carrying mobility of the 3,5 materials, but still grow them directly on a silicon substrate, which is cheap and which is well established in industry. Or in other example where we can use the optical properties of the 3,5 materials, for example, very strong light absorption. This is a photovoltaic application here where we have indium phosphide nanowires in a PIN doping configuration. And then there's a bottom and the top contact. And we can make use of the absorption probabilities that the wires behave like an antenna. And the other, and we can also make use of the small footprint so that it's possible to stack different materials on top of each other, by that tailor the band gap, and with that the optical wavelength that we can use, and still do that without defects in a very efficient way. But for all these possible applications of these devices, the influence of the surface is very important. Since we have these nanostructures with such a large ratio of surface to volume, and if you consider that electronic effects at the surface easily can penetrate 10, 20, up to 50 nanometers into the material, and if our material is only 50 nanometer in diameter, it only consists of surface, if one wants to say so. So the device performance really can be determined by the surface, and we need to characterize it. How can we do that? Well, a traditional method for characterizing surfaces at the atomic scale is scanning tunneling microscopy, which has been developed for flat, homogeneous surfaces, which is more or less the opposite to what we have with nanowires with these high aspect ratio structures. So how can we do STM on these? Well, now everyone who is a grower among you should not watch, because we are doing these terrible things that we break off these almost perfectly grown wires, deposit them more randomly on a suitable substrate, because then we can use our STM tip. If we have the wire lying on the ground, we can climb up on the side facet and just scan on the side facet of a nanowire, which then again is a flat surface for us, as you can see in this example here. The other challenge is that these 3,5 materials have been carried through air, so we need to take care of the native oxide on the surface and clean the wires from that. For that, we use atomic hydrogen at elevated temperatures. And depending a bit on the material, some are easier to clean, some are not. We can be lucky to get images like these, where you can see individual atoms here, arsenic atoms in this example here, lined up in different orientations on a side facet of such a nanowire. And if we have a surface for itself, okay, that might be interesting. More exciting is it if we can have different type of surfaces. And here these nanowires give a special opportunity, since it's possible to tailor the crystal structure of these materials. We can have the cubic zinc blende structure, which we get for all bulk 3,5 materials. But we can also get the hexagonal Wurtzite phase, which is only stable for these nanostructures, for most materials at least. So then we can get special nanowires from our growth experts, which have tailored along the growth direction with the different crystal phase, with different side facets as well. And then we can go along such a wire with our STM tip and come from this example here is one of these hexagonal Wurtzite 10-10 facet over a cubic zinc blende 110 facet, which is well known from bulk structures, back to another type of Wurtzite side surface 11-20 here. And these surfaces have not been known before, because they are not stable in bulk for these materials. And maybe what is of special interest is then the interface between these different facets. As you can see here, this was the growth direction of a single nanowire here. So we can come with our STM tip here, move along one side of the nanowire, move here from a Wurtzite area over the very smooth, atomically smooth interface here onto a zinc blende area and back onto a Wurtzite area. What you can see here are individual arsenic atoms on the surface, plus some contaminations here. So it's a real STM image. And what is special about this here, you can even go 30 degrees across the edge and see some other facets here on the side. And once we know where we are structurally, and then we can distinguish the different areas here on the nanowire from our images, we can also learn something about the electronic properties. We can use our STM tip, place it on either of these different facets, and map the local density of states. By that, we can directly compare the LDOS of the well-known zinc blende structure with that of the rather new Wurtzite facet here in these nanowires. This is what we measure with our doing scanning tunneling spectroscopy on the Wurtzite part here, the hexagonal one, or on the zinc blende segment. And you can see that there is a shift between the spectra. And that is because we have a band alignment, which is here a type 2 band alignment, so that we have a small shift between the valence band edges, and also a larger shift between the conduction band edges, which is important for transport measurements, because it means that there is a barrier if we want to send electrons in the conduction band here from the zinc blende material into the wood side material. How well can we resolve these electronic properties? What is the spatial resolution? If you look here carefully, you can see here is one stacking fault within this nanowire. Again, this is the growth direction of our nanowire. This is an SDM image. You can see here atomic rows. This is a hexagonal structure. But in here, we have one atomic double row of wood side stacking. So this is the zinc blende stacking in this wood side matrix. So that's the smallest possible insertion of a different crystal phase which we can have here. And since we do this have done these SDM images here at low temperature, we have very high stability, so we can place our SDM tip specifically at atoms of our choice and take spectra directly here at this zinc blende insertion, or 1, 2, 3 nanometers away. And we can see as long as we are on the hexagonal wood side area, we have the kind of the same footprint in our spectra and our density of states, but only directly at this stacking fault, so at this small insertion, we have a different arrangement of peaks and generally the elders that we have here. So we can see a transition in the electronic properties from wood side to zinc blende, even on the sub-nanometer regime. And since we have such a small structure here, we even see quantization effects, as we see an apparently larger band gap if we have only a single stacking fault due to quantum confinement in the valence band in this case. All right, what else can we do with these crystal phase heterostructures? We can use them as a template for growing materials on top. In this example here, what you can see here is an SEM image. These are, again, gallium arsenide nanowires, which have different crystal phase, again, have wood side and zinc blende, alternating segments. And what we did with these surfaces, we cleaned them, and then we exposed them to a small amount of bismuth atoms, less than half a monolayer of bismuth atoms. And you can see here in this image, these bright dots, these are bismuth atoms. Otherwise, we have rows here of arsenic atoms. So we can see, okay, these bismuth atoms get incorporated into the surface. They replace arsenic atoms. The height difference here in this SDM image is only about 40 to 50 picometers. So it's much less than an atomic height. So it's really, the atoms are inserted in the 3-5 matrix. But they are not done in the same way, depending if we are on zinc blende or on wood side. Because on zinc blende, we see individual bismuth atoms more or less randomly distributed over the surface, maybe some clustering here close to step edges. But if we are on the wood side facet, we see beautiful nanostructures, as the bismuth atoms like to sit together, forming two-dimensional islands of gallium bismuth or one-dimensional chains of gallium bismuth here at the edges. And this gallium bismuth is material, again, which is not stable on bulk structure. So if a new type of material, and we have this very nice self-selective formation here of an 1D two-dimensional or two-dimensional nanostructures, depending on the crystal phase that we have. Here's a nice 3D rendered image of the same structure. Okay, let's now move to a different type of heterostructure, and that here these are indium phosphide nanowires with PN junction. As I showed in the introduction, they can be used for photovoltaic photovoltaic devices. This is an SEM image. Here we have an SDM overview image. We have the n-dope part here, the p-dope part there. And if we then take spectra all along this nanowire, every nanometer, again, take a new spectrum and plot this, put them all together, we can directly see, we can monitor here our band alignment. So we see the depletion zone where we have the transition from n-type to p-type, and we are surface sensitive. So that also means why we have a rather small built-in potential here, since at the surface it's pinned, so we only have 0.5 electron volts. And you also see that the transition zone, the depletion zone here, is confined to a very small area, so it's only 50 nanometers here where we have the transition from n-type to p-type. We can compare these measurements to a different type of technique. In this case, this is AFM and Kelvin probe force microscopy. So AFM shows the topography, so we have a very smooth and homogeneous nanowire. If we then look at the surface potential with Kelvin probe measurements, we can see a transition here in the surface potential between the n-doped and the p-doped part. But if we measure this is only 0.3 electron volts, the same sample as before. This is because these AFM measurements are done in air, so we have a water film on the surface, which gives even stronger pinning of the surface potential. That's why we measure the bit smaller interface here. And the third option to look at these samples is photoemission spectroscopy. But this here is photoemission spectroscopy at a nanofocus beamline, meaning we can place our nanowire here between, in this case, two gold electrodes with an insulating gap in between. And we have an X-ray beam, which is focused down to 100 nanometer in size. And then we can scan our sample with a nanowire through the beam. So we get element-specific images of our nanowire. We can look at the indium distribution here. We can also look at phosphorus, or we can look at the material of the substrate, in this case here, the gold electrodes, and we can see them where the nanowire now only produces a shadow. So we can take images, or we can focus our X-ray beam onto either the p-doped or the n-doped segment and take spectra, standard XPS spectra, as you can see here. And we have a shift then, if we are looking at indium or if we're looking at phosphorus, we have a shift of the binding energy position due to the different doping, since the core levels that we see in XPS directly follow the band alignment also in the valence band and conduction band. And again, we have a surface potential change here of 0.5 electron volt. We are back in vacuum at clean surfaces. And the reason that we put the nanowires here on separated electrodes is that we can now apply a bias between both sides. Then again, move the wire through our beam and take individual spectra within the distance of 100 nanometers, and we can plot them together. This here is for the unbiased case, where you only see the built-in potential of the nanowire between the p-doped and doped area that we have here, the depletion zone. And then we can, as I said, we can apply a bias between both ends. And that's what you can see here, that we get either a larger potential change under forward bias conditions, or we get a smaller potential transition here under backward bias. So you can do this while we are biasing our nanowire. We would like to do such operando measurements also with the STM. Then the challenge is, okay, we need to bias a single specific nanowire. We can do that, for example, here with cold contacts. Find that wire with our STM tip. Okay, that's a challenge, but that can be done. And then also we need to place our nanowire on an insulating substrate, otherwise it would be shortened. Then we can no longer use STM. We need to combine it with AFM so that we can also scan first on an insulating substrate. Ideally, we can combine both methods, AFM and STM, with a so-called Q+ tip, which is sitting on a tuning fork. So first we go to AFM mode. We take overview images, low resolution images here, only to see, okay, where are our electrodes? There is a nanowire between. We can zoom in a bit here. The nanowires that we have used here are such heterostructures. So it's an Esaki diode consisting of a gallium antimonide and indium arsenide. The gallium antimonide part has a bit larger diameter. That's what we can see here again in the AFM image. And the nice thing is, since we have these electrodes to this wire, we can do a standard transport measurement. So put our bias between both sides, vary that bias and measure the current through the wire. And we get the IV properties here of a nice tunnel diode or Esaki diode in this image. And then now that we know where we are, we place our tip on this conductive part here of the nanowire and switch to STM mode and take scanning tunneling spectra as before. So we get the local density of states at the indium arsenide part or at the gallium antimonide part at the surface. And we see this does not look like an Esaki diode at all. They are overlapping. We have it's a type 1 structure. It's not a broken gap. So we see it's actually the same nanowire in this under the same time that we take these measurements. So we can see how the surface properties can be very different band alignment to what we have in the bulk. That's probably due because we have a very thin quaternary shell here on these nanowires. But still, we can go along in the nanowire with our tip, take spectra here, and see as we move over from the gallium antimonide part with a bit larger band gap. Then here we have the material interface where we have depletion of interface states, and then we get the smaller band gap due to indium arsenide. And finally, what we can do here, since we have the contacts on, we can apply a bias to our nanowire. What we show here is a topography image, an STM image again, where you see from the height difference until where we have the gallium antimonide part, where we have the indium arsenide part. And here in the lower row, what we show is the potential at which we have lowest current. In other words, it's the local, the energy of the local Fermi level. And if we have an unbiased case, shortened wire, we have an equal distribution here of our Fermi level. If we now put a negative bias to our interface, we can see that the bias drops sharply at the material interface. If we put a positive potential on our interface, we can see that the interface is now is open and that the potential drops along the ohmic potential along the nanowire, the gallium arsenide part in this case here. And this is possible because we have the contacts here on the nanowire while we are doing our STS spectroscopy. So let me conclude. I hope I could show you some glimpses of what we can do when we look at the surfaces of these nanostructures of the semiconductor nanowires, even at the atomic scale, where we can combine the surface structure, atomic scale surface structure, with the electronic properties of the surface. We can even modify surface if we want, and we can even look at these under applied bias during device performance. There are many people involved in the measurements, and also we get samples from many collaboration partners. I want to thank our funding agencies. I want to thank the organizers of this conference for inviting me. And first of all, I want to thank you for your attention.
Thank you so much, Dr. Rainer Tim, for your wonderful talk. There is no question from the audience side. We are running out of the time, so I would like to thank you to moving forward with our next presenter, Dr. Yin Bao from the ETH Zurich, Switzerland. He's going to talk on color tuning of single fluorophore emission via polymerization mediated charge transfer. Dr. Yin, the floor is yours.
Thanks for your introduction. Because I uploaded the video, could you just play the video?
Sure.
Thanks. Exhibited a great potential in different type of applications, including biomedical or optoelectronics, such as the light emitting device, fluorescent sensing, the fluorescent encryption, and bioimaging probes, because of the biocompatibility and also the flexible synthesis of the polymeric or organic systems. So it's essential to tune the fluorescent color of these materials for different applications and also for the fundamental research. So normally we can achieve this multicolor vision by either the fluorophore derivatization or the fluorophore combination. So for the first stage, normally you can manipulating the intramolecular don't accept charge transfer by modulating the chemical structures. And for the second strategy, normally you combine different fluorophores to achieve different colors. Recently, there is a system called through-space charge transfer polymers developed by the group of Professor Wang Lixiang. And by using two different types of monomers as electron donor or electron acceptor, by tuning the different chemical structures, this through-space charge transfer between the donor monomer and acceptor monomer can be manipulated, resulting different emission colors. So normally they are based on the design of two different monomers. And this strategy was also further developed by other groups. So we can see this system including the dual fluorophore strategy, like you have two different fluorophores, one as donor and the other as acceptor. By the chemical design, you can achieve the variation of the emission color changes. So we are thinking, because for the design of this complex monomers, it requires multi-step synthesis. We want to think about a simpler strategy, but also can produce the systematic emission color manipulation. So we propose our strategy based on the single fluorophore through-space charge transfer polymer. So we would use the fluorophore or the fluorescent molecule as a initiate for polymerization, and we choose the commercially available donor type monomers as the donor for through-space charge transfer. So by this method, we can just use very simple polymerization strategies to tune the emission color of the solid-state polymers. So we first use the naphthalene diimide as the fluorophore scaffold. We functionalize the fluorophore with two ATIP initiating groups. So interestingly, this molecule is AIE active. We can see on the organic solvent is non-emissive, but in solid state or aggregate state is highly emissive. And importantly, we observe this different emission of this molecule in aromatic solvents when we increase the electron donating ability of the solvents. We can see there is a significant redshift from blue to yellow when increasing the donating ability. And when we perform the ATRP based on this initiator using different type of monomers, also with increasing electron donating ability, we also see the polymer matrix showed the redshift solid emission. So this is similar to our observation in the aromatic solvents. And all of these polymers are AIE active and depends on the electron donating ability of the monomers. We can see they show different colors. And we observed a phenomenon is that when we prepare the blue emissive polymers, we sometimes also can observe the yellow color of the emission. But this is hard to control. Then we carefully revisited the characteristic data of the polymers. We found that during some polymerization and high temperature, this bromo group at the end of polymer chain can be reduced or can be removed during the polymerization and form this vinyl benzene structure. And this vinyl benzene structure can act as a stronger electron donor than the monomeric units, and induced a new through-space charge transfer state, and then alter the fluorescent colors. So we control this conversion of the N group by the specific reaction. We can see when we increase in the conversion of this N group, we can see the color of the polymers changes from blue to yellow-green, and this is very well correlated to this N group effect. So we also tried different chain lengths of these polymer systems. When increasing the polymer chain length, we found that this N group effect was reduced, because when we increase the polymer chain length, the N group and the fluorophore is further than the short polymer chains. So this charge transfer efficiency was decreased. This is reasonable. Then we also investigated other systems. We also observed the similar phenomena. With increasing the N group conversion, we can see the more significant emission color change. And this emission color change is dependent on the polymer chain length because of this through-space charge transfer. So this is not difficult to understand. Even in the molecular structure, the donor and acceptor is far from each other. In the solid state or the aggregated state, they can have much higher possibility to interact with each other. So the both intra-chain and interchain through space charge transfer could be more efficient than the soluble state. That's why we don't observe this type of emission in the organic solvent, but only observe in the solid state or the aggregate state. Then we further use the TDDFT to calculate the ground states of these polymer systems by using a simplified models, including only 4 repeating units for each type of polymer. We can see for the system, both before N group and after N group transformation, there is increasing of the Home energy when we increasing the electron donating ability. And more interestingly, when we perform the debromination step, we can see the Home orbitals migrated from the polymeric units to the N groups. This can induce a significant increase of the Home energy and further induce the fluorescence emission. We further use molecular dynamics simulation in combination with the TDDFT to calculate the excitation wavelengths of the aggregate model from our system. So we can see after the debromination in this aggregate model, there is a dimer structure formed between the NDI fluorophore and the N group transformation induced the vinyl benzene structure. And this structure can induce a significant redshift of the system. So this is responsible for the emission color variation. So because of this through space charge transfer. Then to achieve even a simpler strategy to achieve different emission colors, we performed the one-step polymerization and the higher polymerization temperature. Then we can achieve different polymer chain length and also high level of the N group conversion at the same time. So by this method, we can change the emission color by simply increasing the molecular weight. We can see the color change from the yellow to blue, and the emission wavelength is almost linear with the repeating units of the polymerization. Then we further use a versatile photolithography method to confirm this mechanism of the N group effect. We perform the film preparation by this polymer with vinyl benzene group to form a yellow-green emissive film. Then under the mask with a ETH logo shape, we perform the UV irradiation on the film and form this ETH logo with blue light emission because the vinyl group was broken by the photo initiation. So this can confirm further the N group of our system. So overall, based on this single fluorophore through space charge transfer polymer system, we have 3 different ways to tune the fluorescent emission color in the solid state, either by changing the monomers or by the transform the N-chain groups, or just simply tune the molecular weight of the polymers. So now I come to the conclusion. Based on the previous research, we developed a general strategy for tuning the multicolor emission of polymers in solid state. This is based on the single fluorophore through space charge transfer system. And we observe this unexpected N-group transformation that can induce molecularly remote donor acceptor interactions. And we believe this strategy could have wide potential applications, both in biomedical application and optoelectronics. And recently, we found that this strategy can be used to expand the tunability, expand the emission color from blue to red and even near-infrared region. And with this, I want to thank my students for performing the experiment and also our collaborators for the modeling, and especially for my boss, Professor Rankristoluru, for the great support, and also the financial support from ETH Zurich, the FCG Foundation, and the Swiss National Science Foundation. And with this, I want to thank you very much for your attention, and I would be happy to answer any questions. Thank you very much. Bye-bye.
Thank you so much, Dr. Jinian. I have a question about the colors, how much is the life of these colors, with the passage of time, or if you pass it to for the number of scans of the photoluminescence, how much is sustained its original colors?
Okay, thanks for your question. So do you mean the photostability of the polymers?
Yeah, right.
For this, we didn't test yet, but normally, because this polymer is based on nephthalene diimide fluorophore, normally this fluorophore is considered as quite photostable fluorophore. But for the entire polymer system, we didn't investigate yet because we didn't choose a specific application yet. But this will be, I think, the next step. Thanks.
Thank you so much. Next, our presenter is Dr. Amit Sahe from University of Putra, Malaysia.
Thank you, the organizer, AAFM UCLA 2021, for inviting me to this online conference. My name is Amit Sahe bin Amir Hamzah. I am from Nano Biotech Group at University of Putra, Malaysia. So this year is our 50 years anniversary of establishment of the university. Today I will present the discussion about detection of small targets using Heteroligon functionalized plasmonic particles. So this is a general schematic overview of biosensing challenges. So this graph is made by using affinity as the x-axis and molecular size at y-axis. You go to the right, you get a stronger and stronger affinity. You go up, you have a bigger and bigger molecular size. For example, you can see at the right top corner, which is avidin and biotin interaction. Avidin being a biotin being a capturing agent, and avidin being the target molecule, which is a quite big molecule as a target. We also have antibody antigen interaction at the a big circle over there, which have a lower affinity, much lower affinity, but size of a medium to big size molecular target. Or if you go from there to a little bit down, we have a peptide protein interaction. So protein being a lot of many proteins ranging from probably smaller size to mid size and big size protein. And you can see if in the green area where mechanical based biosensing method, something like QCM or AFM or cantilever based detection method that detect the very presence or the mass of the molecular target, or at the yellow area, which if you use optical base like SPR or LSPR, it can detect the presence of the molecule as well, but this is with refractive index changes. And also if you go down there, electrochemical method can detect using not the molecular mass or refractive index, but using molecular charge, by which say if you use electrochemical method, you can detect small molecule with a big difference in charge. You can do detection very well. But if you use other methods, it is very, very difficult to detect small molecules. So this is, I think, is a big challenge, because metabolites, for example, important molecules, small molecules, they are very small. It's very hard to detect, and this is now our challenge. Mercury, for example, is very small target. Either you pick mercury 2 positive ion or methyl mercury, it is very small to be detected, and it can come from major anthropogenic activities like gold mining and the burning of fossil fuels. And once it is deposited to aquatic environment, it can stay there for a very long time. So it is important to have it monitored from time to time. In our approach here, we use plasmon coupling technique. Some of you might be familiar with this technique because this is a very established technique. Gold nanoparticle in its dispersed condition, it will show you a red color of solution because it absorbs a lot of blue light, as you can see in the absorbance graph. But in its aggregation condition, it will absorb a red light and will show you a blue color. So these changes, we call it a red shift, where you can see a shift. So we make 4 ligands, as you can see here, 4 peptides ligand, and we immobilize them into a gold nanoparticle, and we want to see which ligand can specifically capture mercury 2 ion. So in this picture, you can see peptide 3 and 4 can specifically capture mercury ion and does not capture other metal ions. So this is a monoligand system where we only use one ligand onto the nanoparticle. So after this, we will combine the ligand of peptide 3 and also peptide 4. So we will put it onto different nanoparticle, and we will combine them, and this is called a heteroligand system. The design of the tripeptide is based on Actun motif, where lone pair electron from 4 nitrogen in the middle will be used to trap the metal ion, and thiol group from the middle cysteine will be used to anchor the bonding between peptide and gold nanoparticle. So the idea of using heteroligand instead of monoligand is to have the aggregation between two kinds of modified nanoparticle, and at the same time we can reduce the straight hindrance between the ligands.
So this is a absorbance ratio where you can see if we only use a monoligand system, we have a good signal on the mercury for both peptide 3 and also a monoligand system of peptide 4, where you can see peptide 4 reveal a clearer signal. But if we use heteroligand, where we mix the gold nanoparticle with peptide 3 and also gold nanoparticle with peptide 4, we mix them together and detect mercury, it will show you a bigger, in fact, a bigger signal. We further look at TEM image, what happened to the nanoparticle. So figure A and B is the monoligand system, where you can see the aggregation is not as good as when we use a heteroligand system, where you can see a really compact aggregation to that happened with the gold nanoparticle.
To see at a more macro level of the aggregation, we use a dynamic light scattering to measure the size. You can see the first two lines is a control, which is either bare nanoparticle or just nanoparticle with modifications, but it does not show you any aggregation. But if we use a peptide 3 to detect the mercury, it will show you the aggregation between two nanoparticles, and also for the peptide 4. You can see here both show you the size of 55 nanometer, but in heteroligand it will show a more compact size, which is 51 nanometer.
So what else can we do? Because peptide 3 and peptide 4 bind to mercury in slightly in different way, so we can immobilize, for example, a peptide 4 on small nanoparticle, which in this case 20 nanometer, and peptide 3 on a much bigger nanoparticle, in this case is 100 nanometer gold nanoparticle, and we can do this vice versa. So in system 1, when we measure in a DLS, we were measuring the one that you see in the slide, that result the size hydrodynamic diameter of 276 nanometer, which is like the figure that I represent here. And in system 2, where we reverse the immobilized peptide, you can see we were measuring 170 nanometer of hydrodynamic diameter. So we can control the nanoparticle aggregation, control the structure by using different system with the of course the presence of mercury.
We can also use other tripeptide. For example, here in A is GCH peptides, and in B is HCH peptide. Both are monoligands. If you can see in monoligand system, despite cobalt give a strongest signal, there are also other metal ions that give a signal. So you can see if we use a heteroligon, which is the mixture between GCH and HCH peptide, the signal from other metal ions, particularly from zinc ion, which is the second strongest signal, immensely reduced.
So with that, I thank all of you for listening. So this is our team here at UPM at the Nanobiotech lab, and I am on the right. And we also thank the Ministry of Higher Education and Putra Malaysia for the fund we receive for the research. Thank you so much.
Thanks, Dr. Amir. He's not available for answering any question. Let's invite our next presenter, Dr. Yoki Kim Yap from Michigan Technology University. His topic is emerging applications of boron nitride nanotube for advanced electronics and bioimaging.
Hello everyone, welcome to my talk. My name is Yokin Yap and my group is from Michigan Technological University. Today I would like to talk about emerging applications of boron nitride nanotubes for advanced electronics and biomedicine. There are differences between carbon nanotubes and boron nitride nanotubes. Just to name a few, carbon nanotubes are metallic or semiconducting, and they are useful for electronics and energy storage applications, whereas boron nitride nanotubes are wide bandgap, and they are always electrically insulating. Therefore, they cannot be used for electronics applications. These are the disadvantages of boron nitride nanotubes. In my lab, boron nitride nanotubes can be synthesized by chemical vapor depositions. There are other approaches for the synthesis of boron nitride nanotubes as reported by others group. From now on, let me give you a few examples of emerging applications of boron nitride nanotubes. Let us get started with transistor without semiconductor. Modulation of this work is due to several fundamental limits of semiconductor transistor, including high contact resistance at the nanoscale semiconducting channel, high power consumptions due to current leakage, as well as the short channel effect where the conduction length approach the scale of the depletion layer width. What we have reported is that we use boron nitride nanotubes, which has bandgap of 6 electron volt, and of course they are always electrically insulating. By doing so, we are depositing gold nanoparticle on the surface of boron nitride nanotubes, and then we trying to probe using 2 pieces of STM probe on the electronic transport nature across the surface of these boron nitride nanotubes. As you can see, as we decrease the channel length, the current flow versus the bias voltage is start to initiate at lower bias voltages at shorter channel length, which means the short channel effect that being described earlier in conventional transistor is not present here. And we have also demonstrated the gate effect from these devices. Next, let me talk to you about 2D go with optical bandgap. This work is very related to the work that we have just discussed, transistor without semiconductor. For example, you can see that here are the gold nanoparticles that we described earlier, where we are using them to demonstrate transistor without semiconductors. And if you look carefully behind at the side wall of the boron nitride nanotubes, we see some very interesting structures. As you zoom in, you can see some gold atom, one atoms here, and two pieces of the atoms here, as well as crystals where you can see very well crystalline gold atoms aligned in a monolayer manner. According to theoretical simulation that we have performed with our collaborator, we found that two-dimensional gold, which consists of monolayer gold atoms, become more stable compared to the three-dimensional gold crystal when they are adsorbed on the surface of hexagonal boron nitride, including those of boron nitride nanotubes. This means 2D gold quantum dots become stable on boron nitride nanotubes. We have used UV visible spectroscopy to characterize the differences between the transmission spectra of pure boron nitride nanotubes, indicated by the red curve here, as compared to those coated with the gold nanoparticle, which is shown by the black curve here. As shown here, when the 2D gold quantum dots are coated on boron nitride nanotubes, we start to see sharp absorption band, which indicating that those gold quantum dots are semiconducting particle with optical bandgap in the visible range. In addition, we also found that the shape and the number of the gold atoms per quantum dot can be modulated by irradiation of electron beam inside the transmission electron microscopy. If you are interested on the growth mechanism of these 2D gold quantum dots, please refer to the published work here. Here are the take-home message. 2D gold crystals are less stable than 3D crystals when they are freestanding, but they become more stable when they are supported by or supported on the surface of HBN. Monoatomic thick 2D gold can be coated on boron nitride nanotubes thanks to the cylindrical shape of the boron nitride nanotubes. And from UV visible spectra, we found that boron nitride nanotubes coated with 2D gold feature some sharp absorption spike due to the visible light absorption by the crystal. So electrically insulating and optically transparent boron nitride nanotubes have enabled the detection of this crystal. So as in short, 2D gold crystal on BNNTs are the new semiconductors with direct bandgap. Next, let us talk about transistor by atomic chains inside boron nitride nanotubes. In collaboration with colleagues in Purdue University, we have constructed transistor by tellurium atomic chains filled inside boron nitride nanotubes, as schematically drawn here. You can see that we can fill the nanotubes down to a diameter of 5 nanometer as well as 2 nanometer indicated here. We have compared the transport properties of tellurium nanowires with tellurium atomic chains filled inside boron nitride nanotubes. As shown here, tellurium nanowires are always p-types in transport nature, as also indicated in this graph here, and their diameter are usually larger than 10 nanometer. For atomic chains filled inside boron nitride nanotubes, their diameter are smaller than 10 nanometer, and we shows that they become N-types in transport nature. This is due to the lifting of the Fermi level of beryllium atomic chains inside boron nitride nanotubes that allow the N-types carrier, which is the electron, to become the heat transport agent of the transistor. You can see from here that N-type transistor are showing higher transport mobility compared to the P-types hole. Our results suggested that beryllium atom chains inside BNNTs are van der Waals semiconductors. For example, 5 atomic chains inside BNNT are 2 nanometer in diameter. Transistor can be made by these beryllium BNNT heterostructures thanks to the electrically insulating nature of the nanotubes that will not interfere the semiconducting nature of the beryllium atoms. Ampacity of beryllium BNNT is higher than most semiconductors. So electrically insulating BNNT are the best host materials to encapsulate atomic chains for novel electronics applications. Next, I will talk about the last example that I would like to discuss for this talk, which is a biomedicine applications. This is called high brightness fluorophore. Let us take a look into the simple theory of fluorescent intensity. As you can see that fluorescent intensity depends on the excitation laser intensity, as well as the molar extinction coefficient, epsilon. And of course, it depends on the concentration of the dye of your fluorophore, as well as the geometrical excitation length and quantum yield of the fluorophores. So as a physicist, we look into numbers as well. So for example, quantum yield itself, right, is always range between 0 to 1, whereas epsilon, which is the molar extinction coefficient, it can be tuned between 10 to the power 2 to 10 to the power 6, which means if you would like to produce high brightness fluorophore with very high intensity, it is much more cost effective to trying to work on how to increase the molar extinction coefficient. Let me show you how we use boron nitride nanotubes to enhance the molar extinction coefficients of our fluorophore. We use boron nitride nanotubes as the carrier of a series of dye molecule and an antibody. By doing so, this whole fluorophore will be able to specifically recognize the biomarker on blood cells. The nature of boron nitride nanotubes, including electrically insulating and optically transparent property, can prevent the quenching of this dye molecule. And we can load as many dye or as few dye as we want. And this can be done by non-covalent labeling. Since these structures are chemically inert, the high brightness fluorophore constructed by this manner are biologically compatible. We are using this high brightness fluorophore for blood cell analysis using the technique so-called flow cytometry. As shown here, blood cells consist of many types of biomarker. In short, we call them crustal of differentiation, CD. Here is a brief description about flow cytometry. In this case, blood cells are specifically labeled with fluorophore of different color according to the biomarker that you are interested. Laser light is used to excite all the fluorescence such that all the fluorescent signal on different biomarker can be collected in a same measurement. By doing so, comparing the intensity of different fluorescent signal, one can quantify the population of different biomarker on a blood cell sample. Here is an example of flow cytometry data. In this case, first, we measure the fluorescent signal of CD4 as labeled by a commercial available PE dye, which is one of the brightest dye that currently being used for flow cytometry. As you can see here, the intensity of the PE dye detected here is about 309. For the case of high brightness dye, the CD4 biomarker is labeled with the high brightness fluorophore, and in this case, the brightness is 4 times brighter than those of the PE dye. In fact, in this case, we are using 588 times lower dosage of the high brightness fluorophore. This means in a 1-to-1 basis, each high brightness fluorophore is a couple of thousand times brighter than each PE dye. Alright, in short, this is the summary. A series of emerging applications have been demonstrated based on the unique electrically insulating, optically transparent properties of boron nitride nanotubes. So we have discussed about transistor with a semiconductor by gold nanoparticle coated on boron nitride nanotubes. We have also discussed about the discovery of 2D gold quantum dots on boron nitride nanotubes, and they have tunable optical bandgap in the visible spectral range. We have also used boron nitride nanotubes as a host material to encapsulate beryllium atomic chains, and we found that the electrically insulating boron nitride nanotubes enable the construction of transistor and allow current to flow through the atomic chains without interfering. Last but not least, I have discussed with you about how we make high brightness fluorophore by using dye-functionalized boron nitride nanotubes. So all these are based on the unique properties of boron nitride nanotubes, which have been viewed as the negative properties, which are not very useful for conventional applications. But if you think carefully, some of these so-called negative property at the nanoscale may lead to new discovery or new applications. With this, thank you for your attention.
Let's thank our presenter, Dr. Yoki Kin. He is not here to answer your question. I will pass your query to him to have you the answer. Now, our next presenter is Dr. Irina Derivensek-Olenek from University of Ljubljana, Slovenia. She is not here. We will start her recording presentation.
Good morning to everyone. First of all, I would like to thank the organizers for inviting me to this conference to present here our work. That's a work on magneto-responsive surfaces for manipulation of light and liquid, and this is a cooperative work between the University of Ljubljana, Josef Stefan Institute in Ljubljana, and between East Bavarian Technical High School in Regensburg. The work is focused on magnetic composite materials. And before I explain you our composite material, I would like to remind you of two other composite materials that you very probably already know. First of these materials are Magnetoreological fluids. These are colloidal suspensions of micron-sized magnetizable particles in a non-magnetic fluid. Typically, this is an oil. And they form this very nice flower-like structure when they're exposed to magnetic field. So that's why one can very often see them in science centers or in different science festivals. Another such type of magnetic composites are magnetic rubbers. These are materials that we know from magnetic stickers, and they are also present in the gasket for sealing the doors of our refrigerators and so on. And these are magnetized particles which are embedded in a typical elastomer matrix, which have a Young modulus of several megapascal. And what about our properties or our materials? These are magnetoactive elastomers, which are also known as magnetoreological elastomers, and they have micron-sized magnetizable particles which are embedded in a very soft elastomer matrix. This matrix has a Young modulus below 100 kilopascal, and it's soft like human skin or even softer. And what is very specific about magnetoactive elastomers is that they have experienced very large changes in their mechanical and other physical properties as a function of magnetic field. For instance, where they are out of the magnetic field, they behave like very soft rubber balloons. But when they are exposed to magnetic field, they actually become like plasticine, or like a putty, they become plastic. And in between low and high magnetic field, they strongly change the shear modulus and the Young modulus as a function of magnetic field. This increase in the values of the shear modulus can be several orders of magnitude. And this effect is known as the giant magnetoreological effect. What is the reason for such giant changes induced by the magnetic field? The main reason is restructuring of the magnetic filler particles. The filler particles are typical soft iron, like carbonyl iron microparticles embedded in a poly-DMS matrix. And so these particles are spherical of different sizes. Typical size or diameter is several micrometers, and they are, in the absence of magnetic field, isotropically distributed in the polymer matrix. But when magnetic field is applied, they start to form chains of these magnetized microparticles, and this chain formation actually changes and affects the mechanical and other properties. And we can see here on this image that also surface, of course, can be changed due to this restructuring in the volume of the material. And we are actually interested in this surface modifications. And what can be so interesting, if we can change surface with a magnetic field, this can be, for instance, used to tune optical properties of the surface, such as reflectivity, or we can tune wetting properties for different liquids, such as contact angle, surface tension, and contact line pinning. And we will also show you that also droplet splashing characteristics can be tuned. For instance, corona splashing versus the normal deposition of the droplet. We believe that this is not the end of the story, of course. There are many other properties, so we believe also adhesion properties are strongly modified with magnetic field. Some surface patterns can be formed, which then can also be changed by magnetic field. So there is still a lot of playground available in this field. So here I would like to switch now to our research. So we are using, as I already mentioned, carbonyl iron in the PDMS matrix. Typical concentration that we are using is 70 to 88% of microparticles, and the recipe for the preparation is fabricated since some years. And they have such a shape of disc with the diameter of 20 millimeter and the thickness of a few millimeters. And we apply magnetic field by simply using a permanent magnet, which is moved by a translation stage closer or more far from the sample. And so by this way, we can change magnetic field between about 0 and 1/4 Tesla. So first property that we were analyzing was a modification of optical reflection from the surface. These materials, they are very shiny, but when we apply magnetic field, this shiny, glossy surface become opaque. And so we can see here the transition, which is showing us that at low magnetic field, we have a specular reflection of the laser beam from such a surface. And this specular reflection is, by increasing magnetic field, transformed to spread reflections. And we were analyzing the spreading angle as a function of magnetic field. And we have seen that the spreading angle is increasing with increasing magnetic field, reaches a value about 5 degrees in the quarter of Tesla field, and then it decreases if magnetic field is decreased. And by this information about the spread reflection, if we know what is the lateral diameter of this surface hills that are formed on the surface, and we can get this information from optical microscopy of the surface, we can then calculate the surface roughness. So we make the analysis for different sample, and here we see, for instance, for 78% sample, we can have modification of surface roughness from about 20 nanometer at very low magnetic field to about 300 nanometers when magnetic field is a quarter of Tesla. So if one would extrapolate this analysis, we would expect that one can get a RMS roughness of about 1 micrometer in the field of 1 Tesla. Another interesting property is that also a total reflectivity of this material is decreasing. It decreases by increasing magnetic field. So in the beginning, we have mainly PDMS surface, so we get about 8% of the reflectivity, but when we increase magnetic field, the reflectivity in total drops below 1%. So we were also investigating how chemical composition of our samples affects these properties, and so we have found out that softer the sample are, larger are the surface optical modification in reflectivity and also in the spread reflection. And we also observed that a lower concentration of microparticle gives more and larger changes than higher concentration of microparticles. So one needs soft matrix and some optimal concentration of microparticles for this property. Another thing that we were investigating, another phenomenon, was surface wetting properties. We all are aware that surface roughness, of course, can have an effect on the wetting characteristic, and that rough surfaces are typically hydrophobic. So we expected that if we put water on the surface of our magnetoactive elastomers and then we apply magnetic field, we know from previous study that surface roughness increases. So the idea was that the contact angle will also increase and the surface will become hydrophobic. And we were analyzing such droplets and applying different magnetic fields to our sample and measured contact angle with respect to the surface and the radius of droplets, which were a very low volume, so they had spherical shape. And we came actually to some surprising observation in 2 experiments. In the first one, we were depositing the droplet on the surface in the low magnetic field. We were increasing magnetic field and decreasing it again, and we observed that actually the contact angle was larger in the lower magnetic field. Then we also made an opposite experiment. So we put a droplet on the surface when the surface was exposed to magnetic field. Then we removed the surface, applied the surface again, and we can see here is a jump up. So the contact angle increases, it increases when magnetic field is lower. So the effect is just opposite to what one would expect. And so we were a bit puzzled for some time with this effect, but finally with precise inspection of the sample surface under the microscope, we could get an idea what is the reason, namely that when magnetic field is applied, this carbonyl iron particle actually protrudes to the surface. And this causes chemical modification on the surface. So water, which is in zero magnetic field, mainly in contact with PDMS, comes more and more into contact with our carbonyl iron particles. And because we use particles which have no surface coating, and carbonyl iron is known to be very hydrophilic, so with protrusion of the particles, actually the contact angle decreases. And so we made some analysis of this effect, and we found out that in the field of 230 millitesla, about 6% of surface contact area is modified from PDMS to carbonyl iron. So the third effect that I would like to present you is the effect of magnetic field on magnetoactive elastomer, which indirectly also modifies the splashing characteristic of droplets on the surface. Here we use ethanol, which was dropped onto the magnetoactive elastomer surface from different heights. So it was the droplets were falling on the surface with different velocity. And we will characterize this phenomenon with the so-called Weber number, which is actually the ratio between the kinetic energy of the droplets and the surface energy of the droplet. And we were observing how this ejection sheet is increasing in size as a function of time and as a function of magnetic field, and also whether there are some secondary droplets which produce splashing of the liquid over the surface. And first effect we had observed was that actually the ejection sheet deceleration is drastically changing with magnetic field. We have nearly a factor of 2 larger deceleration in the 300 millitesla magnetic field. Another property which was also very interesting for us to observe is that when the magnetic field is very low and we have some reasonably height from which the droplets are released, we have very nice deposition of the droplet on the surface. So droplet falls on the surface, it makes a tiny sheet of water on the surface, and then this sheet is collecting back into the droplet form, and no additional splashing takes place, so the droplet does not make wetting further on the surface. On the other hand, if we apply to magnetic field, for instance, about 300 millitesla, with the same conditions, we observed a lot of secondary droplets. So the ethanol was splashed all over the surface. And we were then investigating how the characteristic Weber number at which this transition from the nice deposition to splashing deposition takes place. And we observed that with increasing magnetic fields, the typical Weber number at which the splashing starts to take place is reduced. So here it has a value about 200, and here definitely below 180. And so if we now plot this on the x-axis, the Young modulus of the material, for which we know that it is modified by the magnetic field, and we plot this critical Weber number as a function of Young modulus, we can see that by increasing the Young modulus of our material, by applying it to magnetic field, then we can tune actually the droplet splashing characteristic. And this we can do with one and the same material. By, for instance, this group from University in Oxford, which published some similar research some years ago, they were fabricating several different material with different compositions. And they observed a similar effect. So by this, I would like to come to the conclusion. So main conclusions from our work that I would like you maybe to remember is that surface roughness of soft magnetoactive elastomers can be dynamically tuned by variation of magnetic field, and that we can typically get a root mean square roughness in the range of 1 micrometer per Tesla, which can be also reduced when magnetic field is switched off. Another thing is that magnetic field induces modification of chemical composition of the surface. So due to the protrusion of magnetic microparticles, surface chemical structure can be modified. And this is another possibility of regulation, because by changing the surface coating for microparticles, we can then also modify this chemical modification. Both effects strongly, of course, influence optical reflection properties and also wetting characteristic on the surface of magnetoactive elastomers. And the last thing is that tuning of droplet splashing is also possible on magnetoactive elastomers because magnetic field causes modifications of material stiffness. Besides this, we believe that, of course, modifications of surface roughness and chemical composition definitely play a role also in droplet splashing, but these effects still need to be investigated in the future. With this, now I came to the last slide. With the last slide, I would like first to acknowledge my co-workers from my group in Ljubljana and at Jožef Stefan Institute and at University of Ljubljana, then several people from the Regensburg in Germany, and also people from the group at the Faculty for Mechanical Engineering at University of Ljubljana. I would also like to acknowledge the funding for our research, which is from the Slovenian Research Agency, and I would like to thank you all for your attention.
Yes, thanks, Dr. Irina. She is not here to answer any question. while taking the advantage, we will move towards our last presenter, Dr. Shin Ichishimoto from Comprehensive Research Organization for Science and Society, Tokai, Japan. He's going to talk on neutron scattering on yttrium iron garnet under ultrasound injection. Dr. Shin, the floor is yours. You can share your screen.
So could you show my video?
I don't think we have your video in the Dropbox.
Oh, okay.
Yeah.
So then I'll show you my video. Okay.
I'm Ichishimoto from Comprehensive Research Organization for Science and Society. I also belong to National Chenku University, Japan Atomic Energy Agency, and RIKE. First of all, I'd like to thank organizers for giving me a chance to talk about our recent results here. So today, I talk about neutron scattering of yttrium iron garnet under ultrasound injection. Let me introduce our collaborators briefly. Akashi is a specialist of ultrasound measurement. Matsura-san is an instrument scientist of DNA at JPAC. Ieda-san is a theorist in JAEA. Let me acknowledge these people for discussions and their help. And this work was supported by Iketani Science and Technology Foundation and Kakei. Here is the outline of my talk. First, I'd like to introduce ultrasound detected by X-ray diffraction and the neutron spin echo spectroscopy. Then I'll show you experimental setup at the neutron spectrometer DNA. This research has been carried out as a long-term proposal 2017 L300 at JPAC. Then I'll show you results. We observed magnon intensity enhancement by ultrasound injection, and then found anisotropic spin lattice coupling. Finally, I'll summarize my talk. Here is ultrasound effect on X-ray diffraction. This solid line is a black peak of silicon. This black peak is enhanced by ultrasound injection. The enhancement is simulated based on the linear gradient crystal model here. So this enhancement can be attributed to the effect of dynamical scattering. During ultrasound injection, ultrasonic strain field can be observed as a standing wave like this. So typical wavelength is sub-millimeter of ultrasound. Here is ultrasound effect on neutron spin echo spectroscopy. Neutron spin echo spectroscopy is very powerful tool to distinguish elastic scattering and elastic scattering. This is longitudinal mode is applied on silicon crystal. So with increasing voltage of ultrasound, number of photons increases linearly. On the other hand, elastic signal doesn't change so much. Similar result is also observed in the transverse mode case. So we can attribute ultrasound injection to photon injection. Spin-Z effect is observed by acoustic spin pumping of ultrasound on yttrium iron garnet. This light blue shaded region shows negative spin-Z voltage induced by ultrasound. Therefore, we selected yttrium iron garnet for our sample. Yttrium iron garnet is known as a perimagnetic insulator with this subunit cell. There are two types of magnetic moment site. The ratio is 3 to 2, resulting in a perimagnet. we observed 220 magnetic black peak position. This black peak includes small amount of nuclear component like this, but it's much smaller than this magnetic component. Similarly, nuclear black peak 642 also has small magnetic component like this. Again, this is much smaller than this nuclear black peak component. By the way, we have studied yttrium iron garnet. During this study, we first succeeded to measure full spectrum spin wave of YIG. We reported in this paper. Here is the inverted geometry spectrometer DNA at JPAC. Because of this geometry, this spectrometer has very high resolution. That is become 1.5 microelectron volt. This energy corresponds to 363 megahertz in ultrasound frequency. Here is the experimental setup for experiment. We have grown 2 rod crystals of YIG. The rod direction is parallel to 001 or 111. This rod crystal is set in this unit sample cell for neutron scattering. And the magnetic field applied by a pair of permanent magnets. The magnetic field becomes 0.1 Tesla. This is large enough to remove all magnetic domain walls in YIG. Here is scattering plane. Magnetic field direction was always perpendicular scattering vector 0 to -2. On every measurement, we checked ultrasound echo signal like this. So this large echo signal certifies high quality of our YIG crystal. Before showing you our inner neutron scattering result, let me show you energy momentum space of YIG. Because YIG is ferromagnet, parabolic magnum dispersion appears here. Although the anisotropy is very small, by applying magnetic field, Zeeman energy gap opens like this. So the size is about 11 microelectron volt at 0.1 Tesla. At the gamma point, in addition to the magnum dispersion, there are longitudinal acoustic phonon dispersion and transverse acoustic phonon dispersion. So there are crossing points, so-called magnum polarions here. Then we apply ultrasound with this energy. So this energy is very small within this energy gap. Then we measure this energy range, magnum by DNA, neutron spectrometer. We measured this gamma position at the low Q region. Therefore, we observed only magnum part. Here is a summary of our result. There are 4 ultrasound modes. The ultrasound frequency ranges from 21 to 113.5 megahertz. Field circles are measured under ultrasound injection. Open circles are measured without ultrasound injection. So by ultrasound injection, this intensity is enhanced. Basically, for these 4 low temperature measurements, All results shows enhancement by ultrasound injection. On the other hand, right-hand four figures taken at about 140 Kelvin, these results shows only tiny enhancement. So this enhancement was very small. At zero energy, we observe quasi-elastic neutron scattering component, so-called quads. At the same time, at a finite energy, we measure inelastic neutron scattering component. Later, we will compare these scattering components. We also measure the nuclear black peak of 642 at this ultrasound injection condition. As you see, nuclear black peak doesn't change so much by ultrasound injection. Estimated increase 3% is within the error, and the width also doesn't change. So induced change by ultrasound injection can be attributed to magnetic effect. Temperature dependence of enhancement ratio is shown in this figure. Open circles are measured by quasi-elastic neutron scattering. This open circle doesn't change so much with increasing temperature. On the other hand, filled circles measured by inelastic neutron scattering. These enhancement ratio are strongly suppressed at 140 Kelvin, like this. So we can conclude these scatterings have different origins. Inelastic neutron scattering can be originated from magnon. On the other hand, quasi-elastic neutron scattering come from black peak with dynamical scattering effect. So here is inelastic neutron scattering enhancement ratio at low temperatures. As you see, this enhancement ratio is the largest, observed at the 001 longitudinal mode case. So we observed anisotropy between 001 and 111. And in addition, longitudinal mode enhancement is larger than transverse mode case. So there are these results here. So let us discuss this. So this large enhancement was observed under the magnetic field along 001. So let's see the magnetic field direction case in this magnetic hysteresis of YIG at 10 Kelvin. As you see, this red line is the hard axis. So 001 is the hard axis. So magnetic crystalline anisotropy becomes maximum at the 001 direction, suggesting the largest spin orbit coupling. This is very consistent with our result. We observed strong spin lattice coupling under this condition. So second is longitudinal acoustic mode effect is larger than transverse acoustic mode effect. Induced magnetic moment in magnetoelastically coupled equations can be written as follows. In the case of longitudinal acoustic mode, induced magnetic moment is proportional to the elapsed time. On the other hand, in the case of transverse acoustic mode, the induced magnetic moment is proportional to the square of the elapsed time. Because the elapsed time is short, so this induced magnetic moment in the longitudinal acoustic mode can be much larger than transverse acoustic mode. So we may see large enhancement in the longitudinal acoustic mode case. Let me summarize my talk. We observed magnon intensity enhancement by ultrasound injection at low temperatures. Then we found anisotropic spin lattice coupling, especially 001 longitudinal mode is the largest effect. Next is the longitudinal mode effect is larger than transverse mode effect. Finally, the combination of in-elastic neutron scattering and ultrasound effect can be a good tool to probe spin lattice coupling. Thank you for your attention.
Thank you so much, Dr. Shin. Like considering the time limit, like I just have one short question. Like, do you have like the potential application for like these specific structures which you are making and moving forward, or what do you see in future for these wonderful research? Where you are heading up?
So YIG is already known as already applied for many fields, but so for this just we are searching research direction. So yeah, thank you for your question.
Thank you so much. This is the closing for our like. I would like to appreciate everybody for being here to make this session successful. And now I would like to transfer the rights to the Professor Alex Anzer for the next session. Thank you so much.
Thank you. Thanks very much for sharing this session.